So we're going to start our review with just a general review of functions. Today we'll be talking about some terminology related to functions, and tomorrow we'll be talking about terminology related to the graphs of functions. So we want to talk about 4 ways to represent a function. Those are in tabular form, or a table of values, a graph, verbal description, or a function rule, and we'll see all of those in what we're doing today. We're going to work on defining and representing functions and finding domain and range. So we'll start with the definition of a function. Just as a reminder, everything on the screen, all these definitions should be reminders. A function is a relationship between two variables in which each value of the independent variable maps to only one value of the dependent variable. Each x maps to only one y, or the x's can't repeat. The domain of a function, remember, is the set of all possible input values. So that is, it's a legal value for x, that when we substitute in that value of x, we get back a value for y. The range is the same notion as domain, except for applies to y values or output values. Notice that domain and range are alphabetical, and so domain is input, range is output. The notation for a function, I doubt you've forgotten that, but we see the name for the function like f, and then the independent variable like x here, or the name of the function g, the input variable is n, and so forth. Remember that the vertical line test is a graphical test for a function, and that says no vertical line may touch the graph in more than one point, and if it does, then the graph is no longer a function. That's just a graphical description of the definition. And finally, zeros, roots, and x-intercepts are all those words mean the same thing, and they're the values of x that make y 0. So in order to find zeros, roots, and x-intercepts, or x-intercepts, you set y equal to 0. So looking at some sample problems here, how can functions be represented? The first way is by a rule or formula. A little bit of algebra review here, as well as some function notation. So in example 1, we want to find and simplify f of a plus 1. So I'm going to substitute a plus 1 in place of x in both sides of the function. Notice that it says and simplify, so I'm going to do a little algebra here. It's nice, a little bit of algebra review. Remember that if I see a plus 1 squared, I can't just square a and square 1. I actually need to multiply it out by FOIL or some other square of a binomial formula. So a times a would make a squared plus 2a plus 1 minus 2. Remember, I'm going to do my power first and then my multiplication. Again, just a little bit of algebra review because it's been a while. 3a squared plus 6a plus 3 minus 2. And I end up with 3a squared plus 6a plus 1 as my final simplified answer. It's fine to leave the answer in this initial form, but since it said find and simplify, then I need to simplify it down to the expanded form. Part B asked me to find the zeros. That's using the terminology we saw on the last screen. So to find the zeros of f of x, I remember, I need to set y equal to 0. Solve for x. Another little bit of algebra review here. Remember, in order to solve x squared, I need to square root both sides. And when I do that, I introduce 2 possible solutions. I get plus or minus the square root of 2/3. I'm going to leave it that way unsimplified, and I'm going to do that all the way through the course. So there's no need to rationalize that to get that square root of 3 out of the denominator. Second question here presents the function in a different way using a table of values. It asks us to use the table below and the fact that g of x is related to f of x to find g of 2. So this is kind of a combination of reading a table and a function rule. So the first thing I'm going to do is substitute in 2 in place of x in both the label and the definition for g, f of 2 minus 2 squared. Then I'm going to follow normal order of operations. So 2 minus 2 is 0. Squared is just 0. So my right side then is f of 0. F of 0 I'm going to retrieve from the table here. This says f of 0 when x is 0, f of 0 is negative 3. So I end up with 3 times negative 3. So my final answer is negative 9. Sometimes we see functions presented to us verbally. This is a good example of a verbal description of a function. And so about my trip to work, I left home at about 7:15 when traffic was light, but I'd forgotten my lunch, so I had to turn around and go back, and on my way back there was much heavier traffic, so I could not move as quickly. I had to go more slowly. And I'm being asked here to sketch a graph of my distance from home as a function of time. Notice this language here as a function of. That means it's always y is a function of x. So this tells me what my independent and dependent variables are. So as a function of, whatever follows that language is always my independent variable. So that means time is my independent variable here. My distance from home is my dependent variable. And I left at 7:15, so I'm going to say t equals 0 is 7:15 a.m. And then I'm going to start drawing my function. I don't really know from this problem how far away from home I live, or how far away from home school is. So I can't put a reasonable kind of set of scale here on my distance from home or my time. I don't know how long it takes me. And so I'm just going to kind of sketch it in. I start at home at time 0, and then according to the way this reads, I'm moving along pretty quickly. So I don't just start out going the same speed. I kind of start out slowly, and then I have to speed up. Then I realize, oh no, I've forgotten my lunch. So this is me kind of turning around. I'm pausing here. The distance from home is not changing over time. Then my distance from home is decreasing because I forgot my lunch. I'm back at home. I'm probably at home for a few minutes there while I run in and grab my lunch. And then I start back. Again, I start slowly, and this time I'm moving more slowly, which means as time increases, my distance from home is not increasing as rapidly. And then presumably eventually I get to school. I don't know exactly where that is on my, my scale here. But notice the difference in the slopes of these graphs, that when I'm moving rapidly versus when I'm moving slowly. When I'm moving rapidly, the slope of the graph is greater than when I'm moving more slowly. Then a little bit about domain and range. So remember that domain sometimes is difficult for students, but really we're just going to assume that all functions can allow x to be anything except typically for these three kinds of functions. Rational functions are fractions. And so you're thinking, when you're thinking in terms of domain, you're always thinking what x can't be. And I know if I have a fraction, then what I'm going to think is I can't divide by 0. So I'm going to use that rule to then inform me about x, and we'll do examples on the next screen. For a square root function, well, what can't I take the square root of? So square roots, I can't take the square root or even root of a negative number. So I'm going to use that rule in order to help me decide what values I can substitute in for x. And then we'll talk about piecewise functions on their own. Sometimes piecewise functions have a break in the definition for the piecewise function, and sometimes they don't. Let's look at a couple of domain. Let's look at an example of a piecewise function. These tend to be more difficult for you. So a piecewise function is, the definition of a piecewise function is just a function that's defined in two parts over its domain. So the graph changes in some fashion. In the piecewise function that we have here given as an example, we have a linear function for part of the graph and then a quadratic function for the other part of the graph. And so the linear function applies for x values that are less than or equal to 1, so on kind of the left side of the graph. And the quadratic function applies for when x is greater than 1. I like to do, if I'm asked to graph piecewise functions, I like to do those graphs from a little table of values. So here's my little table. I'm going to do 2x minus 1 first. And this tells me what x values to put in my table. It says x needs to be less than 1, and I'm always going to choose the switchover point there as part of my table, even though when I graph it, that point won't be included. So I'm going to choose 1 and then a couple of numbers that are less than 1. Substitute them into my function definition there, 1, negative 3. and then I'm just going to plot those points. So I have 1, 1. I'm going to have an open circle on 1, 1. And that's in red there. It doesn't look like it's exactly on 1, 1, but it's supposed to be. Because 1 is not in the domain of this function, x has to be less than 1. 0, negative 1. I'm going to make a closed circle there because that is a point on the graph. And then negative 1, negative 3. And then I know that's supposed to be a line, so I'm just going to connect the dots there. And there's that function. Now I'm going to do the quadratic function. So f of x equals x squared. This tells me to choose x values that are greater than 1. Again, I'm going to start with 1, 2, 3, 1, 4, 9. And then I'm just going to plot these points. And again, x is greater than 1, so I have an open circle. It's at the same place, but it's still open. And then the order pair 2 and 4. And then the order pair 3 and 9. And then I'm going to kind of try to make that look like it should be a parabola. It's kind of hard to make it a parabola. My scale's bad. But there's my parabola. And then if I were asked to talk about the domain of this function, I can tell from the graph that my domain is all real numbers except x is 1. So I could write that this way. X is not 1. Or I can use interval notation. So interval notation, I start from, it's 2 x values. My leftmost x, smallest thing x can be is negative infinity. It can take all values up to 1. And it can start at 1 and go to infinity, but 1 is not included. The way in interval notation to show that a function of point value is not included is with the soft parentheses or the curve as opposed to the bracket. Infinity always gets a curve because technically you can't reach infinity because I could just always add one more no matter where you are. Then our last example for the day is writing a formula for a piecewise function, so going backwards. This gives us a nice opportunity to review writing equations of lines. In this diagram, I see 4 separate pieces to my function. I'm going to kind of outline those in color. So I have that piece, I have this piece, I have this piece, and I have this piece. So when I go to write my definition, I'm going to have 4 parts to that function definition. So I need a big f of x and a big bracket. So let's work on writing the equation for this part of the piecewise first. So I see that that's a line, and I know that I can write equations of lines in point-slope form. You'll see it's easier. You'll see why in just a moment. This is a form for the equation of a line instead of y equals mx plus b. Some of you may have seen this and some of you may not have. It should be x minus. So if I have the slope and a point, some x and some y, then I can plug it into this form, and that's faster than slope-intercept form, than y equals mx plus b. So I'm going to encourage you to use it. So in this case, my slope, I can just count it. At least I think I can. No, if I can erase. So I'm going to count it, and so it looks like my slope is down 1, 2, 3, 4, right 1, 2. So my slope is negative 2. And I'm going to use this point, so negative 5, 0 is a point on my line. So then to use this form of the equation, y minus the y value is the slope times x minus the x value. Then I can put it in y equals form, and I can leave it that way, or I can make it negative 2x plus 10. That function definition is good for x values starting at negative 5 and ending at negative 3. So I'm going to note that over here in my domain. Then I'm going to do it all again. So now I'm going to do the light blue section of the graph. I'm going to find the slope for it. Its slope is 1, 2, 1, 2. So its slope is 1. And a point on that particular little segment is negative 1, negative 2. So my equation then is y minus the y value is the slope times x minus the x value, or y equals x plus 1 minus 2, or x minus 1. And that definition is good for x value starting at -3 and stopping at -1. Notice that -3 is included in both of these. That's because I can't tell which of those graphs that point's on, and actually it's on both of them. And so I can include that -3. There's no open circle there. And then we'll do one more together, this guy. So that slope is 1, 2, 3, 1, 2. And a point on that line is, oh, that's convenient, 0, 0. So I've got that one, y equals 3 halves x. And that's true from 0 to 2. And then finally, the little horizontal section here, the slope there is 0, just as a reminder. And that's the constant function y equals 3. And that definition works for x's between 2 and 5. And I have my full definition of my piecewise function. Okay, that's it for today.